All right, folks, finally, we've come to area under a curve. We've learned all about sigma notation, and we're going to use that soon. But now we get to discuss this idea of calculating the area under a curve by building a sum of areas of little rectangles. And then as we make the number of rectangles approach infinity, then the area is gonna, like the area approximation is going to get closer and closer to the exact area. And then when we take a limit, then we'll be able to calculate that exact area exactly. So let's start with the idea. We have a function y equals f of x. Down here is our x-axis. Okay, in this example right now, I'm assuming the function is positive. Later, we're going to talk about what happens when the function is negative. If it ever dips below the x-axis, then that changes things slightly. But for now, let's just assume it's always positive. So we have an interval from a to b. We have to have an interval. If we have, well, actually, we don't. Sorry. In Calc 2, you'll learn what to do if you want to take like the area under an entire curve over its entire domain. That is a thing you can do. But for this semester, we're only going to do this with a finite closed interval. So I'm going to start making a list over here on the right-hand side of things. So we have an interval, and that's a to b. Okay. We have a function, and that is our f of x. Okay, that's what defines this curve. Now, what we need to do is take this interval and split it into subintervals. And on each subinterval, we're going to build a rectangle. So let's say in this example, we're going to do this with 4 rectangles. You don't necessarily have to make all the subintervals the same length, the same width, but we're going to. Okay, just to kind of simplify things. There's a number of things here that technically you don't have to do, but I'm going to simplify it down to something that works well. Right? So it works well if you make all the little subintervals the same length. So I've split this up into 4 equal-sized subintervals, and the number of subintervals, which will also be the number of rectangles, it's going to be represented by the letter n. Okay, so in this example it's 4, but imagine that this could be any number, like n subintervals. Now we're going to label the boundaries of those subintervals with some x numbers, x values. So the first one is called x0. So x0 is equal to a. And then the next one would be x1, and then we have x2, and then I'm going to put a ... in here. I would have only 4 with this picture, but imagine that it could be any number, right? So, and then eventually we'll get up to xn, which equals b. So x0 is a and xn is b. There's n plus 1 numbers, but only n intervals that are between them. So now the next thing we want is the subinterval width. The subinterval width is denoted by this delta x. It means change in x. So it's basically this distance right here between two intervals, okay? Between two of these numbers. What we want to do to calculate the value of this is not really just subtract x2 minus x1, because we don't really necessarily know what x2 and x1 are going to be right now. It kind of depends on how many what the value of n is, how many intervals we're making. But what we can do is take the total distance on the interval a to b, that's going to be b minus a, and then divide that equally by the number of intervals we want to make, n. So we're going to use, for delta x, we'll use the formula b minus a, all divided by n. Okay. So now, talking about one of these subintervals here, we can call it the ith subinterval. We're going to introduce the index I to basically label the subintervals. We'll have the first one when I equals 1, the second one when I equals 2, the third one when I equals 3, ... and then we'll have the nth subinterval, which will be the last one. The right-hand side of the nth subinterval is b, the end of the interval, the overall interval. So the ith subinterval basically goes from x sub I minus 1 to x sub I, right? Just look at the first one. It goes from x0 to x1. So the right-hand endpoint of the ith subinterval is xi. And then the left would be xi minus 1, of course, the previous number. So that's the ith subinterval. And then what we're going to do is in every single subinterval, we're going to select what's called a sample point. So we're going to have the ith sample point. Oops, that's meant to be an L. Pretend that's an L. Sample point. That's going to be called Ci. And it just has to be some number which is selected from the ith subinterval. So it's an element of this interval. And these are square brackets because you could pick the left-hand endpoint or the right-hand endpoint. You could pick either of those. So basically, we're going through here in each of these intervals. I'm going to use purple here. In each of these intervals, we're going to pick a C. A C1 for the first interval, and then we'll pick a C2 somewhere in the second interval. We'll pick a C3 somewhere in the fourth interval, ... going down the line. And eventually we'll pick a Cn somewhere in the nth interval. And technically, those sample points can be random. Like the sample points can be randomly selected as long as you select one from each subinterval. Okay? So that's a little bit weird, but yeah, like they could be just sort of randomly selected from each one. However, usually it's easier to come up with like a systematic way of selecting the sample point. And like common choices would be things like using the left-hand endpoints, using the midpoint of the interval, or using the right-hand endpoint. Those are common choices. The most common and easiest to work with is the right endpoint. This is our common choice right endpoints. And for right endpoints, you can actually come up with a formula. And this is a useful formula that we're going to use whenever we're doing a problem like this. So the formula is, what you want to do is start at A, which is the left-hand side of the overall interval. Then you're going to add I times the delta x. Because if you add delta x once, you get to the right-hand endpoint of the first interval. If you add delta x twice, you get to the right endpoint of the second interval. If you add delta x n times, you get to the right endpoint of the nth interval. So if we want to get to the right endpoint of the ith interval, we start with A and add delta x I times. So A plus I times delta x is our formula for right endpoints. So we can use that as a sample point formula when we need some sample point which is convenient to pick, which will be when we're doing when we're actually like trying to like do one of these problems. All right, so the next thing we're going to do is now finally we're going to build rectangles on. Let's see, I'll switch to blue perhaps. We're going to build rectangles on each subinterval. So each subinterval is going to be the base of a rectangle. And the height of the rectangle is determined by the function value at the sample point. So you can see from the sample point C1, I've traced up to the curve. And so now I'm going to make the top of that rectangle at that height. Like that. So my first rectangle is right there. That's going to be called A1. So we're going to have the ith subrectangle area. The area is A1. So the area of the ith one would be AI. Sorry. I think the subrectangle itself is called like R1. And then the area of it is A1. That makes sense. A for area, right? Makes sense. So the way you get that area is length times width, right? Well, the width is delta x, but the height of this rectangle is the function value, right? The point on the curve at C1, the sample point from that first interval. So that would be written as f of Ci times delta x, like that. So let's do the next one. For the next, I'm just drawing what it would look like here for these particular random sample points I picked. That sample point looks like coincidentally to be about the same height as the last one, so I guess it's just going to kind of come across like this, and then it's going to connect down like that, like that. Then on the next one, I drew a little mark here for where that sample point was. So tracing that up, I would put it, find the height of the function on the curve there, and then that's where I'm going to make the top of the rectangle right at that height, like that. And then the last one, would be right there. So that would be something like that. we go. So we have 4 rectangles that we get from 4 different sample points along the curve. And these rectangles are all sort of sitting right on top of a sub-interval, all of which are the same width. They're all width delta x. So here is the formula for the area of each rectangle. And if, by the way, if you are using right endpoints with the a plus I delta x, so using right endpoints, you would specifically get AI is going to be f of a plus I delta x, sticking the CI formula inside there, and then times delta x. So I'm presenting these these as sort of specific choices you could make for the sample point that are going to make the formulas kind of easier. So we'll get back to that. So now what we're going to do is basically approximate the area under the curve by adding up all these rectangles, and we're going to use this formula to add them all up. So area under curve on the interval AB is approximately equal to a sum, I equals 1 to n, whatever n is equal to. You know, if you pick a specific value, you can do that, or you can leave it as n. You can just leave it unspecified. We're going to sum up all of the AIs, right? And so that's going to give us sum I equals 1 to n of the f of CI times delta x. And you can use this if you want, you can use the a plus I delta x for the CI. Okay, this thing here, this is what's called Riemann Sum Approximation. A Riemann sum is the term applied to adding up rectangles like this to approximate area under a curve. It's called the Riemann sum. Riemann was a mathematician who kind of sort of established all the theory behind this, and well, not alone. He based his work on that of a bunch of other people. There's someone who did it before him named Lebesgue, who didn't do it exactly the same way. He did it. Lebesgue had like horizontal rectangles instead of vertical rectangles, but Riemann did it with vertical rectangles, and everybody was like, "Hey, that's easier. Let's do it with vertical rectangles." And so Riemann sum got named after him. So that's what we're going to be doing there. But if we want to find the exact area, what we're going to do is take that Riemann sum approximation, f of CI times delta x, and we're going to take that and take a limit as n approaches infinity, meaning the number of rectangles is going to approach infinity. And that means they're still going to take up this much space. Okay, so they're still going to only go from A to B. But if the number approaches infinity, then the denominator of this formula will approach infinity, which means our delta x is actually going to be approaching 0. So the rectangles are going to get really narrow. Okay, so this whole explanation here is like how this is all the notation, and this is how you actually set up a formula, and this right here is how you do the limit of that formula. This is all building up towards something we call a definite integral, which is the way you solve for the exact area under a curve on an interval. And in the next video, I'm going to show you the definite integral. I'll kind of describe its different parts, and then we're going to go through an example.